This is the one and only video in the Physics Key Skills video tutorial series. Unlike biology and chemistry, physics does not have a key skills section. As such, this video will look over the maths that you need to know for your physics GCSE. In this video tutorial, we will look at how to rearrange equations in order to calculate answers. We will practice conversions between SI units, including using standard form, and we will both describe and explain the information on a graph. Our big question today is to use the following equation, which is speed equals frequency times wavelength. Calculate the frequency of a radio wave if its speed is 3 times 10 to the 8 meters per second and its wavelength is 1.5 times 10 to the 3 meters. Give your answer in standard form. First of all, you need to be aware of the common units in physics. These are meters, litres, kilograms, joules and watts, amperes, volts, hertz, coulombs and seconds, kelvins, newtons, pascals, becquerels and ohms. Meters is a unit of distance, litres of volume, kilograms of mass, joules of energy, watts of power, amperes of currents, voltage of volts, hertz of frequency, coulombs of charge, seconds of time, kelvins of temperature, newtons of force, pascals of pressure, becquerels of radioactivity, and ohms of resistance. You will also come across some other units, for example, centimeters cubed, but we will cover those when they come up in the videos. A key skill in physics is being able to rearrange equations. If we look at a nice simple equation, which is speed equals distance over time. Often, you might be asked to work out either distance or time. In order to rearrange this, there are two main methods. The first is known as the triangle method, which looks like so. Here we have the triangle for speed equals distance over time. So speed equals distance over time. So we have distance over time and speed. If we wanted to work out distance, we would simply cover up the distance, the d on the top, leaving us with speed times time. Time would be distance over speed, and then as we know, speed is distance over time. So, if you're using the triangle method, you simply cover up the part of the equation that you are trying to find. However, we can also rearrange this without using a triangle. This time, if we wanted to make distance the focus of the equation, then we need to get it by itself on one side. The easiest way to do this will be to move time to the left-hand side. In order to do this, we need to do the opposite of dividing, which is multiplying. Anything we do to one side of the equation, we must also do to the other. So to remove time from the right-hand side, we need to multiply it, which means we need to multiply time to the left-hand side, giving us speed times time equals distance, which we can then flip round to distance equals speed times time. Learning this second method is an important skill for your GCSE, as it will enable you to rearrange equations far quicker than using the triangle method. You also don't need to remember a whole range of triangles for each individual equation. Often, equations in physics will ask you to work in standard form. This allows us to write very large or very small numbers without all of the zeros. To do this, we write it as times 10 to the power of however many zeros there are. This makes the numbers far more manageable to work with. In order to do this, we move the decimal point left or right. For example, the number 0.017 can be written as 1.7 times 10 to the minus 2. This is done by moving the decimal point. So, for this number here, 0.017, we have moved the decimal point once and then twice. As we have moved to the right, this is written as a negative number, so -2. The number in front of the times 10 must be a value between 1.0 and 9.9. If, for example, we were to take a much larger number, for example, 15 million. In this number, the decimal point is here. So we're going to move to the left. 1, 2, 3, 4, 5, 6, 7. So in standard form, 15 million will be written as 1.5 times 10 to the 7. I want you to have a go at converting the following numbers. So, for our first number, we need to move the decimal point to the right. We have 1, 2, 3, 4, 5, 6. So the first one would be 1.7 times 10 to the -6. Our second number is very large, so the decimal point will be moving to the left. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 7.4 times 10 to the 14. And then finally, we have our two conversions from standard form. So 3.4 times 10 to the -9 is 0.00000000034, and 8.1 times 10 to the 15 is 8100000000000000. This allows us to use very large and very small numbers in a much more convenient fashion. We can also use standard form to convert between prefixes. So for example, we have meters, which is equal to 1. Millimeters are 0.001 meters, or 1 times 10 to the -3 meters. You need to know several prefixes. So for the smaller ones, we have milli times 10 to the -3, micro times 10 to the -6, nano times 10 to the -9, and pico times 10 to the -12. For much larger units, we have kilo times 10 to the 3, mega times 10 to the 6, and giga times 10 to the 9. These prefixes can be used for any of the SI units. For your physics GCSE, and in fact your science GCSEs in general, it is very important to be able to round to both significant figures and decimal places, and importantly know the differences between them. Decimal place rounding is very, very easy, as you simply round based on the number of figures after the decimal point. So for example, 12.756 to 2 decimal places would be 12.76, as we would round up from the 5. However, if this number was 12.754, then to 2 decimal places it would be 12.75, as 4 is lower than 5, so we do not round up. Decimal places are good when working with numbers larger than 1. However, for smaller numbers, decimal places aren't as useful. For example, 0.0071 to 1 decimal place would be 0.0, and 0.0345 to 1 decimal place would be 0.0 as well. This is where it is more useful to use significant figures. Significant figures only look at the zeros after the first significant figure. So for 0.0071 to 2 significant figures would be 0.0071, as those first 2 zeros are not deemed significant figures. 0.0345 to 2 significant figures, however, would be 0.035, as we would still round up. In your science GCSEs, they like getting you to answer things to 2 significant figures. If we compare these two numbers, so 0.3007 to 2 significant figures, which would be 0.30, and 2.01, which would be 2.0 to two significant figures. I want you to take this number, 0.001023. I want you to write it to 1, 2 and 3 significant figures. So to one significant figure, this would be 0.001. To two significant figures, 0.0010. And finally 0.00102 to three significant figures. You will also be asked to calculate averages. In order to do this, you add up all of the available values and divide it by the total number of values. For example, if the results of an experiment were 10.1, 10.2 and 10.3 seconds, then we would add the three of these together, giving us a total of 30.6. In order to calculate our average, we would then divide this by the total number of values, in this case 3. So we would do 30.6 divided by 3, giving us an average result of 10.2 seconds. However, you will also be expected to identify anomalies. Often in the GCSE papers, they will give you a table of values to work out an average, and they will put an anomaly in there without telling you. An anomaly is a value that doesn't fit with the pattern of the other values. For example, if in the aforementioned experiment we got values of 10.1, 10.2 and 10.3 seconds, and then a fourth result of 5.1 seconds, this would be an anomalous result, as it does not fit with the trend of the other results. When calculating our average, we would then ignore this anomaly and simply discount it when we are calculating our total of values and in our number of values. So for this experiment, if we had a fourth result, which was 5.1 seconds, we would ignore this and our average would once again come out at 10.2 seconds. What we have calculated here is known as the mean average. In maths, you will have come across the mode and the median averages as well. The median average is the result in the middle of the results. So for example, 10.1, 10.2, 10.3, the median result would be 10.2 as it is in the middle of this range, and the mode average is the result which comes up the most often. For these results, they all come up once. As such, we cannot calculate a mode average. Within both your physics and your science GCSEs, you will be expected to be able to both describe and explain graphs. The use of these two words is highly important to what the question wants you to do. If the question asks you to describe the graph, then you need to talk through the pattern of the graph. So for this graph here, which is for distance versus time, if we were to describe it, then initially between 0 and 1 seconds, the distance increases rapidly. It then stays the same for half a second before increasing at the same speed as before up until 2.5 seconds. We then stay stationary for 1 second before moving back to our starting point. This would be an example of a description of a graph. If the question, however, asks you to explain it, then you need to talk about why this is happening. So, for example, in this first section of the graph, we could talk about why the speed is increasing. So the person is cycling hard, causing their speed to increase, and they travel 4 miles in 1 second, for example. We could then talk about why this is stationary, so there is no distance travelled over time, and then what this means as well. So in conclusion of the graphs, if you are asked to describe a graph, you need to talk through the pattern of the graph using the data. If you are asked to explain the graph, then you need to bring in your own scientific knowledge. Graph questions are very common in biology and chemistry as well, for example in the denaturing of enzymes questions, or when we are looking at rates of reaction. Again, these graphs can be described to talk through their shape. For example, the rate increases to a certain point and then drops off. They can also be explained. For example, the rate increases as temperature increases before the enzyme denatures, and then the rate of reaction decreases. For the new GCSE 9:1 specification, you will also be expected to calculate gradients. There are two methods to do this. The first is for a straight line graph, which is the simpler of the two. To do this, we pick 2 points on the graph. So the gradient of the line is the change in the y-coordinate, so the change on the y-axis, divided by the change on the x-coordinate, or the change in the x-axis. Or, if you prefer, the change in the vertical over the change in the horizontal. For our example here, first of all, our red line, the change in the y-axis is 6 from 4, so we have a change of 2, and our change in the x-axis is 1 from 0, so 1. This would give us a gradient of 2 divided by 1, so our gradient of this line is 2. For our blue line, we will have a negative gradient as we are going down to the right. However, if we look at it, the change in the y-axis is -5 minus -2, which gives us -3, and our change in the x-axis, once again, is 1 minus 0, which is 1. This gives us a gradient of -3 divided by 1, so our gradient is -3. In order to calculate the gradient of a curve, we need to draw in a tangent. This is a straight line which touches the curve at one point only. So, for example, this is the tangent of the curve at t equals 10, so when time equals 10. Once we have drawn our tangent, we can then calculate the graph using this same equation, so the change in the y-axis over the change in the x-axis. So, once again, we need to look at our change in our y-axis. So we have 40 and 10, so our change in the y-axis is 30. And our change in the x-axis, we have 15 and we have 0. So our change in the x-axis is 15 minus 0, which is 15. This gives us a gradient of 30 divided by 15, so our gradient equals 2. So, within your physics GCSE, they can ask you to draw a tangent on a graph, remembering it can only touch one point of the curve, and then to calculate the gradient from this. It is also important to note that by drawing a tangent and calculating the gradient from it only gives us an approximate answer. The closer your answer will be to the correct answer, the better the graph and the better the tangent line that you have drawn. Therefore, you will be asked to estimate the gradient of the curve. So, in this video tutorial, we have looked at rearranging equations in order to calculate answers. We've converted between SI units, including using standard form, and we've described and explained the information on graphs. To finish, I want you to attempt today's big question. So using the following equation, speed equals frequency times wavelength. I want you to calculate the frequency of a radio wave if its speed is 3 times 10 to the 8 meters per second and its wavelength is 1.5 times 10 to the 3 meters. I want you to give your answer in standard form. So first of all, we need to rearrange this equation. In order to rearrange it, we need to make frequency the main topic. In order to do so, we need to move wavelength across. At the moment, it is being multiplied. The opposite of multiplication is division, so we will divide wavelength and bring it onto this side. So the equation we need is frequency equals speed divided by wavelength. We can now pop our numbers in. So our speed was 3 times 10 to the 8, and we will divide this by 1.5 times 10 to the 3. Popping this into our calculator gives us an answer of 200,000. This is why it is essential that you have a scientific calculator for your science exams, as you will be expected to use standard form. In order to convert 200,000, we will convert this into standard form. So we have 2 times 10 to the 1, 2, 3, 4, 5. This gives our final answer of 2 times 10 to the 5 hertz, as this is the unit of frequency.